Hi everyone, welcome back. In this particular video, we're going to go over two specific examples of electrophilic aromatic substitution: the halogenation of aromatic compounds and the nitration of aromatic compounds. Now, the halogenation of aromatic compounds is usually done in presence of a catalytic amount of a metal. You need some catalyst to do this reaction. So for example, if you want to do a bromination on any aromatic compound, now again, I'm using benzene as a representative example here, but it can be any aromatic compound. So if you want to do a bromination on an aromatic compound, we will use Br2 along with an ion catalyst, FeBr3, iron tribromide. And that would give us bromobenzene along with HBr as a side product. If you want to do a chlorination instead, we will use chlorine and aluminum trichloride. Now, if you use FeCl3, it is still going to work, but aluminum trichloride is a better catalyst for doing this reaction. So when we react benzene with Cl2 in presence of aluminum trichloride as a catalyst, we're going to get chlorobenzene and HCl as the product. So notice we are making bromobenzene and chlorobenzene as our products here, along with HBr and HCl, which are our side products. Now, fluorination of an aromatic compound, or benzene specifically here, is very violent. Okay, it's a very violent process. So we do not do fluorination this way. There are other reactions that help us make fluorinated aromatic compounds. We will see those reactions later. Iodination, on the other hand, is a very slow reaction. So again, it's not practical. So in terms of practical reactions, the bromination and the chlorination are the reactions that are more practical. So let's look at the mechanism of this reaction, and we will also try to understand the role of the catalyst in this process. So before we get into the mechanism of the electrophilic aromatic substitution, we're going to see the role of the catalyst. So what is the way we understand this reaction in terms of the mechanism is that the bromine or the chlorine, I'm going to do the mechanism or write a mechanism for the bromination reaction, but that mechanism can be extended to the chlorination reaction. So the bromine molecule, in presence of metal catalysts like FeBr3, which we can simply write like this. Okay, we're going to write it like that, the FeBr3. The ion here, this is electrophilic because it's connected to the three bromines. You could think about it like that. And the ion here is actually in a +3 oxidation state because the three bromines are 1 negative each. So that's how the bonding in metals work. So the ion can actually form an interaction with the bromine molecule, the Br2. So this is going to give us an intermediate where we have the Br, and now we have an interaction with the ion, like that. So the formation of this intermediate is now going to land some formal charges on this complex. So we can get a formal negative charge on the bromine and a formal negative charge on the ion and a formal positive charge on that bromine atom. And the formation of this intermediate is going to activate this bromine. So this bromine can take away the electrons, which is going to activate this bromine, and it can give us a Br plus along with an ion which has 4 Brs connected to it. So that's how we generate our bromine electrophile. Now, the bromine electrophile is not formed like an independent species, but this intermediate that we have can be read like this. It is a bromine that is electrophilic here. So essentially, when we have this combination of Br2 and FeBr3, and we have our aromatic compound, so the bromine interacts with the FeBr3 to give us this intermediate. And now the benzene or any other aromatic compound, I'm again going to draw one hydrogen on the aromatic compound. So the benzene or any other aromatic compound, it can do a nucleophilic attack on this intermediate that we have. So it's going to do a nucleophilic attack on this intermediate. So the pi bond is going to come and attack this bromine, the terminal bromine, and simultaneously this electron pair goes to the bromine in the middle here. And so this will take us to the sigma complex. We have H, we have Br, and we have the positive charge here. And along with this, we're going to have the FeBr, 4 Brs with a negative charge. So that's going to form as the counter ion. Okay, so realize that this was part of the earlier discussion here. So the mechanism is here. Now what we formed here, this is the sigma complex. And this is called the sigma complex because we have a sigma bond now between our electrophile and the aromatic compound now. So we've formed that sigma bond. And now this sigma complex can be deprotonated by the Br minus that's in this FeBr3. And when that happens, this electron pair can come down and it would give us the product, which is going to be bromobenzene plus HBr, and along with that, we will have FeBr3. So we have regenerated our catalyst. The ion catalyst is regenerated again. So that is why it can behave as a catalyst, because it can go back and start this process again. Now, the sigma complex that we've made here, this is resonance stabilized, as we saw in the generalized mechanism for an electrophilic aromatic substitution. But it is not necessary to show the resonance here. So the sigma complex is resonance stabilized. But that's the mechanism of a bromination of an aromatic compound. And it can be easily extended to the chlorination by substituting the bromines and the FeBr3 with the chlorine and the AlCl3, the aluminum trichloride. So that gives us a similar mechanism. Next, we're going to look at the mechanism of the nitration of an aromatic compound. The nitration of an aromatic compound, and specifically benzene is the example that we're looking at here, is done using a mixture of nitric acid and sulfuric acid. And this would give us the nitrobenzene. Now, for this particular reaction, the electrophile in this reaction is a nitronium ion, which is NO2+. So this is a species where we have a nitrogen that's double bonded to 2 oxygen atoms and has a formal positive charge on it. So that's the nitronium ion. So in the mechanism here, we're going to first talk about the formation of the nitronium ion. How do we generate that? And as you can probably see, the nitronium ion has to be formed from the nitric acid that's in this reaction. So we're going to start there. So nitric acid is HON double bond O, O minus. This is the Lewis structure for nitric acid. One of the Lewis structures, there's resonance possible here. And when this reacts with sulfuric acid, which is HO S double bond O, OH, the hydroxyl group here, or the oxygen, which is part of the hydroxyl group in this nitric acid, this can get protonated with the sulfuric acid. Now you might wonder why there is an oxygen with a negative charge and why isn't that getting protonated? That can also get protonated. That's equally possible. We're saying is whenever this oxygen, which is part of the hydroxyl group in the nitronium ion, gets protonated, then this reaction is going to move forward, or that is what we want here. So we'll get an intermediate where there is a protonated nitrogen, double bond O, O minus, double bonds, and this oxygen here has a positive charge on it because it lost one of its electron pairs. And along with that, we are going to make this bisulfate ion from the sulfuric acid, the conjugate base of sulfuric acid. Now, this nitronium ion can lose the water molecule because this is now a good leaving group, so we can lose that molecule, and that would basically give us the nitronium ion. Okay, which would give us the nitronium ion plus, sorry, there is a positive charge here on that nitrogen also. Yes, there is a positive charge on that nitronium also, and so that gives us the water molecule. So that is how we generate the nitronium ion. And so once we have the nitronium ion, then benzene or another aromatic compound can react with the nitronium ion. So both of these oxygens have 2 lone pairs each. So the pi bond on the benzene is going to do an attack on the nitronium because this is our electrophile for the reaction. And when that attack happens, this negative, the double bond will get pushed over. And so this will now take us to the sigma complex. So the sigma complex is always formed in the electrophilic aromatic substitution. Okay, we will get the sigma complex. Now, as we've seen earlier, this sigma complex is resonance stabilized. Now, you don't have to show the resonance here, but I'm going to show it so that we can practice it on another sigma complex. So essentially, the pi bond here can move, and that would give us the next resonance form for this sigma complex. Get a double bond, hydrogen, N double bond O, minus, and then we've got the positive charge here. And now the pi bond can move again. So we're doing the next resonance structure. Give us a positive charge here, double bond, H, and NO2, like that. So we get that structure. And this is where a weak base that is in the system. And for this particular case, it could just be the water molecule. It can go and deprotonate that hydrogen from the benzene ring, and the electron pair from that bond falls into the space so that we reform the aromatic ring. So we get the double bond with N double bond O minus. Sorry, I've been leaving out this positive charge. So there is a positive charge on the nitrogen because the nitrogen has 4 bonds to it. So that positive charge is always there on that nitrogen atom. This is still there. That is the Lewis structure of the nitronium or the nitrate, the nitro group, actually, the NO2. So we get this. And so there we have our nitrobenzene product. The NO2 product is formed. So this is our nitrobenzene. Now, if you're wondering, do we have to show the resonance that is possible in the sigma complex? You do not have to. You could show the loss of this hydrogen from the first sigma complex here. So you could use water to deprotonate this hydrogen, and the electron pair would fall into this ring to complete the aromaticity, or make the benzene ring again, to make the compound aromatic again. And that is how we will get our product. Along with that, we are going to have a hydronium ion, which is basically a representative of acid in the system. So that's the mechanism of the nitration of a benzene ring. And the electrophile that's used is the nitronium ion. I hope you find the mechanism of the halogenation and the nitration helpful. We will see other mechanisms in upcoming videos.